So last time we talked about artificial potential field, okay, and we said that we imagine the environment, the map, okay, which is just a map, you know, as objects that attract the robot or repulse it. So if it's an obstacle, it will repulse, push away the robot. If it's a goal, it will attract the robot. Okay, we'll imagine our environment something like this. We're gonna choose or select as a programmer or as a robotics engineer. You're gonna choose the attraction force. You're gonna choose the repulsive force. Take the gradient. Apply what we discussed last time. You know, the new location equal to the old location plus the velocity or the speed multiplied by, you know, something related to the gradient sign, negative or positive, and we usually move in the same direction of the negative gradient because this is a direction that leads us to the goal. There is no need to make, you know, like extra everything, you know, as I will show you with a pretty huge map, very huge map, okay? It's 400 by 600 cells. All the maps that we discussed so far was really, you know, 10 by 10 max. With this large map, in just maybe 10 lines of code, and maybe I can also merge some of them, it will be even less than 10 lines of code, you can get to the goal location. Okay, and no need for a stack and all such stuff, you know, you don't need actually. Okay, so and last time we saw an example of how to move in the negative gradient, you know, negative gradient direction. But there was no obstacle. So it was very simple. You have only goal in your map, okay, with no obstacles. So we have only one function, which is the attractive function. And we see by our eyes, you know, by the coding, you know, that the robot was following the direction of the negative gradient, and that direction basically leads the robot to the goal. Okay, and we say there are some constants or some parameters we can say that we must fine tune them in order to get, you know, a kind of trade-off between the speed of the coding, of the program, and also the accuracy of reaching, at what distance we reach close to the goal. So the first thing we're gonna do today is to extend this example a little bit further to include just one obstacle, just one. Okay, so we have here the same example, exactly the same example, but I added an obstacle at 0. Okay, I didn't draw it, or I forgot to make a slide for it. Okay, but it should be the same slide as before. So if we show you the slides of the last lecture, yeah, it should be the same as this one. So this is the example that we solved last time. You have just 1D example, very simple. You have only the goal at 50, and the robot starts at, you know, sometimes we started the robot from one time from the left, then we started from the right, you know. Now I will add an obstacle at x equal to 0. So something in here. So we can draw it again. Let's do it now. So this is example 1, and this is example 2. Same, exactly the same, but we will have here some obstacle at x equal to 0. And here is Mr. Robot, you know, can start from here or whatever. And maybe this map is also extended to, or longer, I'm saying. Let's decrease this. This is the x-axis, and our space is from x equal to 0, and we have there at x equal to 0, we have an obstacle, and our goal at x equal to 50, and we finish the map. So the space that the robot can move within is from x equal to 1, because the obstacle is x equal to 0. So the map itself is from x equal to 0 to x equal to 100. Okay, so this is our space now. So the robot basically cannot go beyond 100. Maybe there is a wall there, I don't know. Okay, but this is just, example, a made up example, just to make you understand easily the problem. And we have our object at x equal to 50, and the robot may start its journey from here, from the left, or from here, from the right. Okay, last time we have exactly the same example, but without this wall. So at that time we created one force, which is the attraction force. So obstacles come with repulsive force, something to push the robot away. Goals come with attraction force, something to attract the robot to. So let's see. So we have here. So let's see the coding itself, how it goes. Okay, so we have the same stuff. Okay. So the goal is at 50. So the space is from 1. I make it 1. So let's do it as 1 here, just to be, consistent with the coding. At 1, goal is 50. Okay, we need the attraction force. This is basically the same attraction force that we did last time. It was 1 multiplied by x minus the goal location, xg or g, whatever you call it, to the power of 2. And why we use quadratic functions? To have a minimum. It has a very nice mathematical characteristics. You can make the gradient easily with such a kind of functions. Okay, so it has a global minimum, just one minimum. So okay, there is no worries from this function. And if you remember the slides, if we go to the slides here, we say that we may need, where is it? Yeah, we may need some kind of constant, which I call zeta here, or zeta. We may need some constant, and I will show you why we might need these constants. Okay. And I said without showing you an example that we may need this constant to balance, the two forces, to make them comparable. Okay, and we will see that in that example today. Good. Now let's create the map. The first example, the map was very simple. I said there was only the goal. Now we have an obstacle. So we need to create an array. And remember, this is 1D map. It's very simple one, just one line that robots is moving along. And we have our obstacle at x equal to 1. So all the points in the map is 0, which means free. So the cell here is just a point. Okay, it's not a square like 2D maps. And at x equal to 1, or the first location in the map, there is an obstacle. So this is the only location in the map that is true. Okay, good. Now we need something to let us know the distance from the obstacle. Again, we didn't need that in the previous example because there was no obstacle there. Now we need a function that tells us the distance from any point in the map to the obstacle. Okay, I can do that with you very quick. If you, so for example, if you go back here, yeah. So the wall is at x equal to 1. So this is maybe the only, this is the only location that the robot cannot go because there is obstacles there. But it can go to x equal to 2 or 3 or 4 or 5 or 6, whatever, until 100. And at each point of those, we need to know our distance from the wall. So for example, if the robot is at x equal to 2, its distance from the wall is 1 because 2 minus 1 is 1. If the robot is at x equal to 40, then the distance is 39, and so on. You got my idea, right? So in MATLAB, there is a very nice function called BWS, this distance, okay? I don't know what is BW stand for, but I know distance is just distance, okay? So BW dist will give you the distance from, so BW dist of some array will give you the distance for at any location in the array that is false or 0 to the nearest location in the map or the array that has true or 1. Okay, so in our example here, there is only one obstacle at x equal to 1. So the distance, so so we're gonna calculate the distance for x equal to 2, 3, 4, 5 until 100. Okay, so for example, let's run this to make it clearer for you. So let's run this. Yeah. So let's check map. You see, guys, all are zeros except the first element, which represent the obstacle. 0 is free cell, and the cell here is just a point, and 1 means an occupied cell or obstacle cell. Now let's check D. Wow. So D here contains exactly 100 element, or yeah. So the distance, for example, at x equal to 1, or the second element in this map, okay, you see 1 because the distance from to the first element, which has the wall or the obstacle, is 1. At the obstacle itself, the distance is 0, so you have 0 in the first element. At x equal to 100, the last element, the element number 100, the entry is 99, which means the distance from this element or this cell to the obstacle is 99. This is clear, guys, or you have some confusion? Should I continue?
It's clear.
So that's all BW dis does?
Yes.
Okay.
Yeah. Maybe you see it's not that difficult here. Okay, you can do it in a better way. Not a better way. For example, you can do it easily using for loop. Okay, you know that the first element is just 1. But if you have a 2D array with many obstacles, okay, so if you wanna measure the distance at any free cell, you should do it to the nearest obstacle. Okay, so if you have many obstacles, assume you have a point in between, and there is a obstacle here, obstacle here, obstacle. So it's surrounded by obstacles everywhere. So this function, this need function, will do that for you, but it will calculate the distance to the nearest obstacle. So it's really convenient to use it. That's why I use MATLAB for this course. Okay, because it's easy to simulate stuff without going into details. Okay, because if this is C++, you should do that yourself. You should make a function maybe like this, very huge coding, just to do this one line of code. Okay.
Mr. Mustafa?
Yes, Johnny.
Based on what you said, what if there is
like two obstacles at the same distance from
That's
the
fine.
like
So
robot, which one would it choose to calculate the distance?
it will do the, yeah, it will do always. So let's do it. Let's do it. So to not to improvise with you. I know this information, but I didn't test. So let's do it together. So let's add another obstacle. So let's say that what? Yes, map of, for example, 20 is also true. Now the last element, it should have a distance of 89. 89, yes. 89 or I'm sorry, 79. So let's see. Let's see how it work. Because this was information, but I didn't test it. So that's a good question. So let's see. Yeah, yeah, that's right. So basically, you calculate to the nearest obstacle. Okay. So give yourself, a good look for the elements here. So the first element is an obstacle. So the distance to the same obstacle, which is the nearest, the closest, is 0. The second one is closer to this guy. Okay. So check, for example, at cell 19, which is the first element in the second row. This cell number 19, it has just on the cell number 20, it has obstacle. So it calculates the distance to the nearest one, which is just 1, right? If if it will calculate to another obstacle, it should be 19, not 1. The last element, it shows 80, because 80 is this element, which is it's 99 cell away from the element number 1, and the 80 cell away from element 20, which is obstacle right now. So the distance is 80. Okay.
And that would be for the obstacle too, right? Because it's going from 1 to 80. That's 80 away from the second obstacle that you put.
Yes, because the closest obstacle to the cell number 100 is the obstacle at cell number 20.
Right. Okay.
Okay. If we put a cell, if we put an obstacle, for example, at 98, look, the distance is 2, because it calculates the distance to the nearest or the closest obstacle, which at this time it's the obstacle at cell number 98, and 100 minus 98 is 2. Okay. So let's go back to our already, but that's a very good question, really, because we can test it easily here in this map. In 2D, it's really difficult, really difficult. Okay, so if you remember, guys, from last time, we need usually we choose that the effect of the repulsive force to be 0 after some distance from the obstacle. So, for example, if the obstacle at 1 here, okay, we may choose that the effect of the repulsive force to be 0 if we are at x equal to 20, or further, 21, 22, until we reach 100. Okay, but it's up to you. We can ignore this, but I don't know exactly why they do it in that way. This is, again, this is not my coding, but I understood it very, very good, as I believe. Okay, so I think maybe for some examples, this is good for the stability of the function, because you need the gradient, and the gradient, is not, it's easy to get in MATLAB, of course, but the stability of the numbers that you get may not be good if you ignore such detail, which is making the repulsive force 0 after some distance from the obstacle. So let's go what we have. Okay, let's go with what we have. That we will assign 0 for the repulsive force after some distance called d naught or d0. So here I choose d naught equal to 30. Okay, so the repulsive force will have no effect, will be 0 after 30, 31, 32 until 100. Now, you remember, guys, this rho of x, which I said it is just, we cannot put the distance directly, 1 over the distance. Why? Because some of the values may be 0 in D, and this is indeed the case here. If we look at D, some of the values are 0, which is the first one. So 1 over 0 is equal to infinity. So we need to add 1 first to remove this 0. So we can divide by rho. If we divide directly, 1 over, if we say here 1 over D, 1 over the distance from the star, from the obstacle, it's okay. If this array doesn't have zeros. But if it has zeros, then you should make something like this. This is again user choice. Remember, this is not rule. This is not something, sacred that we cannot change. No, this is our choice as an engineers. So to remove such a problem of dividing by 0, we add 1. One may say, can we add half? Yes, you can add whatever number you want. Just remove this 0. Okay. Okay, so this is, if you remember here, this is the actual function, the repulsive function. It's equal to some constant, again user choice, and I will show you the importance of this constant, multiplied by 1 over the distance from the obstacle. And again, we cannot take the distance at itself. We may process it by adding this 1 to avoid dividing by 0. Minus 1 over d2 to square. Why square? Again, we like to make the functions quadratic, so it has minimum and maximum. Okay. Good. And this is eta. This is the constant, which I choose here as 10 to the power 4. Okay, let's see the plotting of each one of these functions, the repulsive force, the attraction force, and the addition of both of them, because as I said, we create a repulsive force which has very high values at the obstacles, like this. We create an attraction force which has minimum value at the locations of the location of the goal. Then we need to add them up so that we combine both properties together in one function that has both properties, high values near the obstacles, small values near the goal. That's why after creating these two here, this FR and also FA in the beginning, I add them up here. Okay, one little detail before adding them up, I said that for distances larger than d naught, which is in this case 30, we want to avoid or we want to neglect the repulsive force. So here we are saying that for any value larger than d naught, 30, 31, 31, 32, 33 until 100, both the FR equal to 0. So let's explore this. So let's continue because it's also already running. So let me run it from the beginning. Yes. Let's look at the values. All the values are non-zeros, as we see. Okay. Now, after executing this line of code, Let's look now at the look. After 30 zeros. So we say by this, the repulsive force is neglected or negligible after a distance of 30 away from the obstacle. So for example, the repulsive force at x equal to 2 is equal to 2177.8. Remember, if each element here is multiplied by 1000, you see there is 1000 in the beginning. 1.0 E3. That means each element is multiplied by 1000. So the repulsive force at x equal to 0 is equal to 2177.8. The repulsive force at x equal to 3 is actually 9000. Okay, or 900. I'm sorry, 900. The repulsive force at x equal how much? 23 is around is maybe 1. Okay. Okay, let's now sketch these functions or plot them. So first we're gonna plot the repulsive force. So look, guys, this is our map now, not this one. Now the map is actually one line, which is this one, the x-axis. And look and observe the values of the F repulsive at each value of x. So it's really, going, remember the obstacle is at x equal to 1. And at x equal to 1, which is this, look, at x equal to 1, y is equal to 9344. It's the highest value. If we go to another location, let's enlarge it. At x equal to 2, yeah. At x equal to 2, it's 2000. So from 9000 to 2000. One good thing here is that that the goal is at 50. And at 50, it's really negligible. It's almost zero. It's zero. It's not almost, it's zero. Okay? So, and this is also a good characteristic of the function. If you use a function, a repulsive function that has a big value near the obstacle, that means it may repulse or push away the robot from the obstacle as well. And this is not required. It should have only high values near the obstacle. So because it's repulsive force. Okay, let's continue and plot the other functions as well. This is F attraction. So in MATLAB you can draw two plots together at the same time. So this is F attraction. So this is the original one, which is F repulsive. The red one is F repulsive, and the blue here curve is F attraction. And you see it has its minimum value, actually 0, at the goal at x equal to 50. Otherwise, it has considerable value. But look here at the value of this F attraction at 1, the location of the obstacle. It's 2400. While for the repulsive force, it's 9344. Okay, so now you expect that if we add them together, the combined force F equal to FR plus FA will have very high value at the obstacle and very low value at the goal. So let's see. Let's continue and plot the total force, the summation of both together. The summation, guys, is this. Oh, How to remove this? That's annoying. Yeah. That's really annoying. But anyways, so yes. Okay, this is the original one. So the red curve is the repulsive force. The blue curve is the attraction force. And this is a summation, which is the black one. The black at some points in that locations here, the black is just on top of the blue, so the attraction force just disappears. Doesn't it's still there, but they have both same value approximately at these locations, from 50 and forward. And look at the black curve now. The black curve has even higher value at the obstacle, and still zero or the minimum at the goal location. Okay, and that's actually what we want, because the robot will move based on the summation of the two forces. Okay, so when it come here near the obstacle, it will see very high force, and when it come to repulse it, okay, so if the robot moves along this slope, the negative gradient, if we imagine that the robot is just a ball, and we put it here at that location, it will slide down, right, until it catches or reaches the goal. That's the idea, by the way, of negative gradient. That if you imagine that there is a ball on your curve, it will go opposite to the direction of the gradient until it reaches the minimum. So just imagine it. If you have a ball and you put this ball here, it will slide along this black curve until it reaches here the minimum and just stands there. Okay, it may make some bouncing but at 50, but it will stay forever there, because this is the minimum. Okay, it's like a gravity. That's it. That's why we have repulsive and attraction force. Okay, so let's continue. This is clear, guys? Any questions? Okay, let's continue now. Good. Again, like yesterday, we said we need some number of iterations, because maybe we will just bounce around the goal. So we need to break the loop after some time. And we need a tolerance to say that, for example, here, if we reach the goal within one cell error, means if we are at 49 or 50 or 51, we're gonna stop because we reached it close enough to the goal. Okay, the tolerance is just the how much acceptable difference between the goal and the current location of the goal. You remember also there was something called speed, and we discovered that this speed is very important. Okay, and we need to fine tune this speed so that we not bounce around the goal with high error. At the same time, if we choose it with high value, we may reach the goal faster. So we need to choose some value for it to run the code faster, at the same time reach with good accuracy to the goal. We will see that in a moment. This is the start goal of the robot. It will start just beside on the obstacle. Actually, it's not correct here. So it shouldn't be at the same cell of the obstacle. So we should choose it at 2. Although the program will run, but physically it's not right. It's not correct. So we should make it at 2. But the program just runs. It will not say something. So the current position is at the start, which is 2 in that case. And here we will put in this array, we will put each point we reach along the x-axis. Then, like yesterday, we calculate the negative gradient, and we say that, for example, for this black curve, the negative gradient will be negative here and positive here. It will be positive here, so we move in the positive x-axis, and will be negative here, so to move in the negative x-axis to reach the goal. So let's continue this. Let's plot the gradient on another. Yeah, this is the gradient. It's pretty much similar to the f function. Okay. I think there is a grid, yeah, it will appear afterwards. Yes, this is a grid. So let's look here. Here we know it should be negative. Look, guys, it's a negative. That means we should move, if the robot is in that location, it should move to the negative, in the direction of negative x-axis to reach the goal at 50. And here it should be positive. Look, this is 0, by the way. So it's positive. 56 positive. That means if the robot is at that location, it should move in the positive x-axis in the direction of positive x-axis to reach the goal, and that's right, because the goal is in here, so we should move in that way in the positive x-axis to reach the goal. And it's, of course, it's very clear here that it's a positive 7,000. Okay. Good. So let's go into our iterations. So look how many lines you have. 1, 2, 3, 4, 5, 6. Don't count these because it's just a drawing. 6 lines of code. Only 6 lines of code. That's why it should be simpler. Maybe it has a deep math background or needs some visualization, but it's really simple. So let's see. We say that yesterday, this is x new equal to x old, which is now current position, plus the speed, which is 1 in that case, multiplied by positive or negative 1. So we don't need the actual value of the gradient. We need only the sign, negative or positive. Here in that, on the left of the goal, it's a positive. Here on the right of the goal, it's a negative. And if we look at the delta direction, just 1 means positive 1. Okay, so there should be a plot now, yes. So you moved 1 cell forward in the positive x-axis. Let's continue. Second cell, third cell, fourth. Okay. When we reach the goal, and in that case we will reach the goal exactly because the step size is 1. It should, boom. Actually, we reached 1 point before the goal because the tolerance is 1. So 49 minus 50, of course, absolute value is 1. So this is acceptable tolerance for us. So yeah. Okay, guys. So this is a very nice and neat example, just 1D. So you can, understand well how we construct, repulsive force, attraction force, the summation of both together. Why this is, working, and how it is simple. It's really simple, as you see, just 6 lines of code. Don't count what's before that just count those. Okay, this is actual thing that will take time. The thing before it just one line and just, you know, execute and go forward, execute and go forward. But here is the thing that will take time, because this is iteration. One iteration means 6 lines of code. If you make 2 iterations, 12, you execute 12. 3 iterations, you know, 18, and so on. So we usually count what's behind what's in the while loop. But whatever iterations it took, it's against just 6 lines of code. Okay, any question before we go to the 2D example? Any question? No question. Okay. Okay, so let's go to the, let's finish this guy here. That's finished. Good. To the 2D example, which is really, you know, complicated. But once you understand the basics, it will be easy. Let's stop here. I will run one run for you, okay? And we're gonna see during this run how it's nice. Okay, so let's see. Just forget about, yeah, let's look at this. Here is the map, okay? These are obstacles, by the way. Here is the goal, and here is our robot, this sliding ball. It's just, you know, a simulation. So this is basically the actual idea. So let's go back to the, it's really nice. So this is actually the idea behind using the negative gradient, that if you have a sliding ball and you shape the map in that way, okay, it's like, since a sliding ball, so it will, you know, go, if it's in a position which is, you know, have high value, so it will slide down to the position with low value, minimum value, which in this case, or it should be all the time this case, it's the goal location. Okay, so that's really cool. If you just imagine the robot as a ball, it will go by itself to the goal location. Okay, just like a gravity, exactly like a gravity. So let's see how we did this. It's not that easy, but step by step it will be good. So let's, you know, skip that guy and skip the debugging as well. So let's see what we are. Okay. So we have here, this is again example that I got from GitHub. Okay. So I get this example from there and I try to build upon, understand it well, and so on. So we have here a map, 2D map with 400 rows and 600 columns. So like a rectangle, not a square, rectangle. Okay, so you have 400 row and 600 column. Then you create an array called obstacle. Basically, this will, you know, define the obstacle locations. So in the beginning, it's all free. There is no obstacle. False means no obstacle. So obstacle equal to false of n rows and n columns. This will create an array for you and fill it with zeros. Okay, so let's do that step by step. Oops, I'm very sorry. I am very sorry. I'm very sorry. Yeah. So let's look at this. It's not even opening because it's really big. So the debugger of MATLAB cannot open it for me because it's really big. So if I just hover over this guy for it, because it's small, just one element, so it shows me the value, but this, because it's really big, it doesn't show anything. But anyway, that's fine. Okay, now we're gonna create, each element in the array has coordinate, right? X and Y. Okay, so using this mesh grid here, we are creating a grid, okay, just like the ones that we saw in our previous algorithms and previous MATLAB codes. Okay, but with this function here, which is called mesh grid, we are returning in that output X and Y, we are returning basically the row and the column of each cell in the array. So basically, let's do it. Just let me explain it on the tablet better. So I will share my tablet now to make it easier for you to understand, because it's not that direct. So let's have any notebook here. You guys can see my tablet, right?
Yes.
Yeah.
Okay. So if you have any array or any grid, so let's have a very simple example. When I say mesh grid of 1 to 3, 1 to 3, which it will create something like this, okay? The output of that command here is another two arrays that you can call X and Y, and basically for each cell, for example, this cell here, its X coordinate will be in that location and its Y coordinate is in that location. So if this is X and this is Mr. Y, okay, so here X is 1, so there will be 1 here. Here, yeah, and the numeration of Y, it began from, yeah, I am very sorry. So it's not that straightforward, but anyways. Yeah, so this is X and this is Y. You remember, guys, MATLAB enumerates cells from starting from here. Okay, so this is our starting point. So here is Y is 1, 2. So Y increasing in that direction. This is the direction of the increment of Y. Why MATLAB is this is MATLAB issue. That's not my issue. He chooses to do that, not me. Okay. So this is basically 1, 2, 3. So here is 1 and 1. This cell here has also X coordinate, which is again 1, and its Y coordinate is 2. This cell has X coordinate of 2 and Y coordinate of also 2. This cell, X coordinate is 3, Y coordinate, I'm sorry, X is 3, and Y coordinate is also 3. Okay, so this mesh grid command here will return two arrays. In each of these are just coordinate arrays. Okay, so the X of that cell in the grid is here in the X array, and the Y coordinate of that cell in the Y array, the same location in Y array. That's it. Okay. Why we do that? You remember, guys, this bad stuff which is convert from index to from index, from ID to index, and the opposite. This is something like this. Okay, but you have now two arrays which contains everything for you. Contains every row and every column. One thing in here is that you will notice that when we create the mesh grid, we put 1 to columns and 1 to rows. And in the first element here is X, and the second element is Y. One may think rows usually X and columns usually, no, it is the opposite. Okay. Oh, I'm sorry, I didn't share my screen. I should share the other one. Okay. So I was just, you see my lab code, my MATLAB, right?
Yes.
So I just get back to here, okay, and there is an observation. So we know now what mesh grid will do. It will create two arrays, okay. The first element in that array is Y. The first element in that array is X of any location in the grid, okay. But we will notice something. The first element here is X, and here is one. Here is the number of columns, basically. Here is Y. Here is the number of rows, basically. So Y is corresponding to the rows, and X is corresponding to the columns, which may not be, intuitive for you, but this is actually the correct thing, correct stuff. So let's go back to the tablet to show you that. This is tricky, I know. So basically, even with our same example here, so X is increasing in that direction, right? X here is 1, X here is 2, X here is 3. But this is basically column 1, column 2, and column 3 at the same row. This is row 1. So basically, X is actually the column coordinate. And Y is increasing in that direction. Here is Y is 1, which is row 1. Here is Y of 2, which is row 2. Here is Y3, which is row 3. So Y is corresponding to the rows, and X is corresponding to the column. Okay? That's why when we go back to the MATLAB code, that's why columns and rows, and here X is in Y. Because X is corresponding to the column and Y is corresponding to the rows. Good. Now this guy was creating some obstacles, okay? And these obstacles has, some fancy shapes. Some of them are rectangular. Some of them is circular obstacles, okay? So let me I will where is it's not here. There is a plot somewhere of this. There is a plot. There is no plot. Or there is a plot. No, there is no plot. Okay. That's fine. So basically, in that part of the code, we are generating obstacles. That's it. We are not doing anything extra. I mean, this is not part of this is not the negative gradient or something. This is just how to create the map. Okay, this is not the artificial potential field. Okay, so here basically in these two lines, it's creating a rectangular obstacle. This is a rectangular obstacle. So we are saying here from row 300 to the last row, which is 400, and the column 100 to the column 250, assign true, which means true means the obstacle, false means the free cell. And from row 150 to row 200, and the column 400 to column 500, true. So again, another rectangle. This is a tricky part here. Here, it's creating a circular obstacle, okay? This obstacle, this circular obstacle, is centered at point, which is 200 in X and 50 in Y, or row 50 and the column 200, and the radius is 50. Okay, before I have a code that explains this, but before going to the code, let's examine something here. How to draw, a circle, just in nature, in just a piece of paper. So if you have X and Y, the circular equation is very simple. So if you have some circle, its center is at X1 and Y1, some point called X1 and Y1, and its radius equal to R. So you just look at X1 and Y1. This is equal to R. So the equation of that curve here, of course, it's a shape, not curve, is as follows: X minus X1 square plus Y minus Y1 square equal to R square. Okay? X1 and Y1 and R are known. So if we want to draw this circuit point by point, we create a kind of table, something like this. X, Y. And all what we need to do is just, putting what? Yeah, both X and get Y, yes. So we just put some whatever values of 1, 2, 3, 4, 5, whatever, okay? And substitute in that equation here, you will find only one unknown. Okay, get this unknown. For example, at X equal to 1, we have whatever Y. So this is X equal to 1, and this is whatever Y. Okay, and you have many points like this. Then you connect them together, you get a circle. Okay, that's very similar stuff in MATLAB. So in our example here, X1 is 200 and Y1 is 50, and the R is equal to 50. Okay, so let's go to the MATLAB again and try to apply what I explained on the tablet. Circular obstacle. Okay, so again, any circle you want to draw in MATLAB, just define the center coordinate X, the center, the column coordinate of the center, YC or Y coordinate, and the radius. For example, 25. Here I am drawing at a circle of radius 25 at exactly the center of the shape of the rectangle, in columns over 2, in rows over 2. Then you define a variable, okay? And you just write the equation here. And you say that obstacle of T is equal to true. Any cell, any cell, any element in the obstacle array that belongs to T is equal to true. The other is false. So this should draw a circle for you. So let's quit up the. So look, guys. So this is actually yes. We have 600 column and the center is at 300. We have again 600 row, and again it's 300 at the, and the radius is 25. If we look here, it's 30, maybe plus. Yeah, this point here is approximately. Oh, we can do it in another way. Can do. That's fine. Yeah. It's really difficult. That's fine. So this is approximately 25. Okay, if you go down here, it's a 25. If you want to change, so let's for example say XC and YC in another location. Let's say is at 100 and 200. And this radius, for example, is 50 or 100. That's fine. Or make this is 200. Make it more to the middle. Let's see. Yes. And let's. Okay, we say that this is the x coordinate. 200. This is 300. Okay. And the radius, if we take some point somewhere, yeah, it's 200. Then that's not exactly at the perimeter, but you got my idea, right? It is how we draw circle obstacle. Okay, so this is an obstacle, for example. All the values here inside all the cells inside this obstacle is part of the obstacle, of course. So that's why we don't say equal, we say less than. We include in the obstacle, it's not just the perimeter. All the point inside this obstacle is belonging to the obstacle. Again, this is not artificial potential field. Okay, this is how to create a simulator or how to create an obstacle, a circular obstacle in your map. Okay, so don't worry if you didn't understand it quite well. Okay, so this is our map now. It's a very simple map. It's either free cells with false or obstacles with true. And here is the function that I was telling you about, which is calculating for any cell the distance between this cell and the closest or nearest obstacle. And we see in one dimension how it behaves, and we tested that it really calculates to the nearest obstacle, not any arbitrary obstacle. So okay, so D should be a 2D array, okay, and it has zeros at some points. These zeros are just points that belong to the obstacle, so the distance to the obstacle is 0. And other points which has values which has some distance from the obstacle. Okay. In the 1D example, rho is equal to D plus 1. Here, this guy has divided by some arbitrary constant, which is 100. Actually, I changed the value. It was something different from 100, as I remember, maybe. But anyway, this is another parameter that you may choose. Okay, together with this eta parameter, which is in that case 1000. And here is D naught. D naught is equal to 2, means any cell 2 steps away from the nearest obstacle, it has just 0, or has a 0 repulsive force, or the repulsive force at points with distance larger than 2 from the nearest obstacle is just neglected or negligible, with value equal to 0. And here is the repulsive force. It's exactly the one we saw in the 1D example, except that rho now is not just d plus 1. It's d divided by some, some arbitrary parameter that again you had to fine tune to a good value. Okay. And then you add you construct this equation, and this is now the repulsive force. And again, just like the 1D example, we say that for any rho larger than d node, the repulsive force is 0. Okay. I'll go back to the one-dimensional parameter, and I'm gonna show you what happens if we change this eta. So with this eta here, let's good. This is the repulsive force, the attraction force, and the total. Okay. Now let's make this eta with 1, just 1. You remember its actual value, it's 10 to the power 4, which is very high. Now just 1. Let's see what's gonna happen. Look at the difference between the repulsive and the attraction force. Actually, the repulsive force, it's just 0 compared to the attraction force. It's just 0. That's why I make it, but I make it 10 to the power. Again, let's read this again to see it. So this is the repulsive force. The maximum value is here. It's around 1, we can say 0.93. Okay, very small. Now, if we draw the attraction force, the maximum of the attraction force is 2,500. So there are very huge difference between both. That's why we need some constant to play with the actual value. So let's make it, for example, 100, and let's see the situation with 100. So now it's 90, not 0.9. It's still, you see, guys, it's still high. So let's try, for example, 1,000. Now it's 900. Yeah, now it's comparable. We can continue on that. Okay. Also, I choose it to be 10,000 to make. To make the values really comparable to each other. So I don't want both some function, some force to overcome other force. Okay. Okay, that's now I think you have some idea why we need those parameters. This eta, for example, which is 1,000 here. If it's less than this, the difference will be very high between the repulsive force and the attraction force that I'm gonna show you afterwards. Okay, so this concludes the repulsive force. Let's just draw it before go to the repulsive force, to the attraction force. Okay. Yeah. Remember, guys, this repulsive force is a 2D function. It's a function of 2 variables, not 1 variable. In the 1D example, the repulsive or the attractive force, or the summation of both, was a function of 1 variable, which is x. Now these functions are a function of 2 variables, x and y. That's why it has a 3D shape, because at each x and y in the map, there is a value for the force, the repulsive force. Okay, and these values are actually, if there is a plot here, no, yeah, these values are actually very high at the obstacle locations. So this is basically the obstacle. This is one obstacle. And you see, guys, it has very high value. It's an obstacle in both x and y. This is another obstacle. This is a circular obstacle. And this is another circular obstacle. Okay, this is another rectangle. So you have two rectangle obstacles and two circular obstacles. Okay. So, and you see that the repulsive force or the repulsive potential has high value near these obstacles. Okay. And flat anywhere else. Just flat. You see? Just flat. So if you have a ball at that location, for example, on a flat ground, we can say it will not move. It needs the attraction force to make it move. But if the ball is in, for example, on that slope, let's imagine this is a mountain, and you put a ball here. So the ball will slide down, but then it's flat here. So it can go anywhere. It will not go to the goal location. That's why we need another function to represent the attraction force. So the robot slide down from the obstacle and slide again to the goal, whatever its location. Okay, so that's it for today. It's really long lecture with a lot of details. So let's continue next time with the attraction and basically finishing this this algorithm. And of course, I will publish another homework which I really lack, which is Dijkstra in C++. But please try to study well the codes for the one-dimensional example, the code of yesterday, and also try to read this code by yourself and try to see the differences between the 2D map or the 2D example and the 1D example. They should be very close. They should be close. What you may encounter not known for you is some functions to draw 2D maps, for example. This is something that you don't know. I will not say I'm sure, but maybe you don't know. Okay, but this is not artificial potential field. So try to read this code. I will publish it today for you. Try to read it with the 1D code and also yesterday's code. Okay, and we will continue on Tuesday. So next Monday, it will be our, first lab. Okay, and this lab is basically to construct and get to know the stuff that you have in your robot kit. So please don't try to construct it by yourself because you may damage it. Okay. So next Monday, we will have our first lab. I need just from you a screwdriver because some parts in the robot kit needs a screwdriver to connect it. Okay. Any question, guys? Any question?
Yeah, I have a quick little question. So that parameter you're talking about, the ETA, would that need to be adjusted for, would it need to be adjusted from going from map to map or just one time?
What is ECA?
ETA, the variable you're adjusting?
Eta. You
Yeah.
can call it eta. It's a Greek letter. So eta is a fine tuning parameter. So it depends on the map, maybe. Okay. So for this map, 1000 is good.
Yeah.
I'm not saying this is the only solution. It may work. Let's try with 1200. Let's try and see.
No, I guess my question is will it need to be adjusted for going from one map to another map? You know what I mean?
Yes.
Okay.
So 1200 basically is working here. It's not bad.
Yeah.
All these parameters that I was talking about is basically depend on the map. Okay. Any other question? And of course, I will see you tomorrow also in the office hours if somebody is interested to attend. Before the lab. For the lab, I just need you to find some screwdriver. You're gonna need it. Any other question, guys? Any other question? Okay, so see you tomorrow on Monday. Bye-bye. Have a nice day.
You too, Professor. Thank you.